Most of you would have experienced a situation where you're looking for some logs and you find them missing and get disappointed. We were experiencing something similar, and today we are here to talk about our experience in scaling our logging infrastructure and how adopting ClickHouse helped us in resolving most of our issues. I am Monica Singh and I have Pradeep here as my co-presenter today. We work as SRE at Cloudflare in Singapore office. In case we go blank, let's blame on the jet lag. Before we dive into challenges in maintaining these logging pipelines, we would like to talk a bit about the characteristics of logs. In today's world where there are a ton of microservices, the amount of logs that a centralized logging server receives is very unpredictable. There are various reasons why capacity estimation of log volume is so difficult. Primarily because new applications get deployed continuously. Existing applications are scaled up and down automatically to handle business demands. And sometimes application owners enable debug logging and completely forget to turn it off. Another characteristic is logs are semi-structured. Every application adopts different logging format. Some represent it in plain text, others represent it in JSON. The timestamp field within these log lines also varies drastically. Multi-line exceptions and stack traces make it even more unstructured. Such nature of logs add extra resource overhead since they require additional data parsing and mangling. Logs are contextual. Most of the time when we are debugging some issues, we need contextual information before and after an event has happened. A single log line hardly helps. It's a group of log lines which helps in building the context. Many a times we need to correlate the logs from multiple applications to draw the full picture. Hence, it's very important to preserve the order in which logs get populated in the data source. Any centralized logging system is write intensive. 99% of logs which are written are never read. They just occupy space for some time and later on get purged by retention policies. The remaining 1% of logs that are read are very important, but we can't predict what that 1% is going to be. So we can't really apply any sampling over these logs. Now that we have looked over characteristics of logs, let's see how a typical logging pipeline looks like. Even though everybody uses different tools to build their logging pipelines, at a very high level, it's mostly the same. Like producers or applications generate the logs, shippers ship them to a centralized queue. Inserters read this queue and write them to a data store. Visualization tools query the data store and let the user slice and dice the data and build dashboards over them. Next, Pradeep will walk us through the challenges with Elasticsearch.
At Cloudflare, we have been running a multi-tenant cluster of Elasticsearch for many years, and it has served us really very well. Over these years, our log volume increased drastically, and while we were optimizing our Elasticsearch cluster to handle such high log volume, we found few challenges. First and foremost, everyone running Elasticsearch must be aware of mapping explosion. Elasticsearch maintains a mapping where it decides how a new document and its fields get stored and indexed. When there are too many keys in this mapping, it can take a significant amount of memory, resulting in frequent garbage collection. In today's microservices world, every application logs its own set of keys. When you have large number of such microservices, the mapping can easily grow too big, resulting in this issue. One way to prevent this is to make the schema strict, which means any log line not following the strict schema will end up getting dropped. Another way is to make it semi-strict. That means any field that is not part of this mapping will not be searchable, but it will still be stored in Elasticsearch. Elasticsearch does not have a very good multi-tenancy support. One bad user can easily impact the cluster performance. There is no way to limit the number of maximum number of documents a query can read, or the maximum amount of memory a query can take. A heavy query can easily degrade the cluster performance, and even after the query finishes, it can still leave its impact. It is not easy to manage big Elasticsearch clusters, especially those which are multi-tenant. Once a cluster degrades, it takes a significant amount of time to get the cluster back to a fully healthy state. In Elasticsearch, updating the index template means reindexing the data again, which is quite an overhead sometimes. At Cloudflare, we use hot and cold tiered storage, that is, we store the recent data in SSD drives and older data in magnetic drives. While Elasticsearch moves the data from this hot to cold storage every day, it affects the performance during the time when the data is moved. Like any other Java application, Elasticsearch also requires some garbage collection tuning. Default garbage collection in the latest JVM is G1GC. We tried evaluating other garbage collectors like ZGC, which helped in lowering the garbage collection pause a lot, but didn't give us much performance benefits in terms of read and write throughput. Let's now hear about the Cloudflare scale from Monica.
To give an idea about scale at which Cloudflare operates, we serve about 35 to 45 million HTTP requests per second, out of which around 500 to 800,000 requests fail per second. These failures can be due to improper request issues or origin server error, misconfiguration by user, network issues, or various other reasons. These error logs are used by customer support team as the starting point to triage any customer issues. The error logs have vast number of fields ranging from client-side information to server-side information to customer information. It also includes metadata about various Cloudflare products that the HTTP request has gone through. We were storing all these error logs in Elasticsearch. We were heavily sampling them since storing everything was taking a few hundreds of terabytes, crossing our hardware allocation budget for this application. Dashboards built over it were quite slow since they required heavy aggregation over various fields. Also, we need to retain these logs for a few weeks as per the team requirement, which were further increasing our storage needs. Keeping all these in mind, we set very clear goals. First, we wanted to remove sampling completely. That means to store every log line. We wanted to improve fast query support over this huge amount of data. And lastly, achieving all of this without increasing cost. Looking at these goals, the first thing that came in our mind was ClickHouse. We decided to do a proof of concept and see if we can accomplish our requirements using it. So why ClickHouse? Cloudflare has been an early adopter of ClickHouse for their analytics requirement, and we have been managing these ClickHouse clusters. We already had a lot of in-house tooling around it and libraries for inserting data into it, which made it very easy for us to do the proof of concept. Let us look at some of the ClickHouse features that make it the right fit. ClickHouse is columnar database, which means all of the data related to a particular column is physically stored next to each other. Such data layout helps in fast sequential scan even on commodity hardware. This enabled us to extract maximum performance out of our older generation hardware. ClickHouse is designed for analytics workload, where the data has a large number of fields which can be represented as different ClickHouse columns. Most of the databases start performing poorly as the number of columns increase. We were able to design our ClickHouse table with a large number of columns without sacrificing performance. ClickHouse indexes work very differently compared to relational databases. In relational databases, the primary indexes are dense and contain one entry per table row. So if you have 1 million entry in a table, then the primary indexes will also have 1 million entries. While in ClickHouse, indexes are sparse. which means there will be only one index entry per few thousand table rows. This not only reduces the index size but also reduces the overhead of adding new indexes. ClickHouse compresses everything by default using LZ4 compression. One of the cool features of ClickHouse is you can configure compression per column basis. This feature enabled us to use the best compression for a particular data type. For example, we use special encoding like Gorilla along with ZSTD compression for columns like timestamp. Having an efficient compression not only helps in minimizing the storage needs but also lets ClickHouse use page cache efficiently. ClickHouse is linearly scalable, which means writes can be scaled by adding more shards and reads can be scaled by adding more replicas. One of the very important features in ClickHouse is it doesn't have any special node. Every node in ClickHouse is identical, and not having any special node helps in scaling the cluster very easily. Having an efficient inserter is equally important as having an efficient data store. At Cloudflare, we have been operating quite a few analytics pipeline from where we borrowed most of our concept while writing the inserter. We use CAP-NP messages as the transport data format since it provides very fast encoding and decoding. Scaling inserter is easy and can be done by increasing the number of Kafka partitions and spawning up more number of inserter pods. One of the key performance factors while inserting data into ClickHouse is the batch size. When batches are small, ClickHouse ends up creating a lot of smaller partitions which it then merges into bigger partitions. The small batch size creates extra work for ClickHouse to do in the background, therefore reducing the ClickHouse performance. Hence, it is very important to set it big enough that ClickHouse can accept the data batch happily without hitting memory limits. Over to you, Pradeep.
Now that we have looked at how the inserter works, let's look at some of the data modeling in ClickHouse. ClickHouse provides an inbuilt sharding and replication without any external dependency. I think there are very less databases in today's world which provide something like this. Earlier versions of ClickHouse used to use Zookeeper for storing the replication information, but latest version removed that too completely. To read data across multiple shards, we make use of distributed tables. It's a special kind of table in ClickHouse world. These tables themselves don't store any data but acts as a proxy over rest of the tables which are storing the data. Just like any other database, it's very important to choose the right table schema since it will directly impact the performance and the storage utilization. We would like to discuss 3 ways in which you can store your logs in ClickHouse. The first one is the simplest, but it's the most strict table schema where you specify every column and their data type. Any log line having a field outside this predefined table schema will get dropped. From our experience, this schema will give you the fastest query capabilities among all. If you already know the list of all the possible fields ahead of time, we would definitely recommend using it. You can always add or remove columns by running the alter table queries like in any other database. The second schema uses a very new feature of ClickHouse where ClickHouse does most of the heavy lifting for you. You can insert logs as JSON objects, and behind the scene, ClickHouse will understand your log schema and dynamically add new columns with appropriate data type and compression. This should only be used if you have a very good control over the log schema and if the number of total fields is less than 1000. On one hand, it provides you great flexibility to automatically add new columns as the new log fields are inserted, but at the same time, one bad application can easily bring down your entire ClickHouse cluster by misusing this feature. The third schema stores all the fields of same data type in one array and then uses the ClickHouse inbuilt array functions to query those fields. This schema scales pretty well even if you have more than 1000 fields, since the number of columns only depend on the number of data types you are using in your logs. If any of the log element is accessed very frequently, you can take it out as a dedicated column using one of the feature of ClickHouse called materialize column. We would recommend adopting this schema since it provides you the right safeguard against application logging too many fields. One of the other important aspects to get efficient performance out of ClickHouse is how you design your data partitioning. A ClickHouse partition is a unit of data which you can move across one node to another within or across the cluster. One of the common mistakes ClickHouse users do is by selecting this partitioning key too granular, which ends up resulting in too many partitions. Since our logging pipeline generates terabytes of data, we create a new partition at the start of every hour. This way, when we query by timestamp, ClickHouse knows the partition having the actual data and retrieves it quickly without looking at other partitions. It also helps in designing efficient data purging rules. As you know, primary key is very important for having an efficient query performance. ClickHouse stores the data on disk sorted by primary key. Thus, selecting the right primary key not only impacts the query performance but also helps in having a better data compression. Unlike relational databases, ClickHouse doesn't require a unique primary key per row, and we can insert multiple rows with identical primary keys. Having a very long primary key will negatively impact the insertion performance. One of the ClickHouse limitation right now is once a table is created, we can't update the primary key. So it's important to select the primary key early in your proof of concept phase. ClickHouse query performance is directly proportional to whether it can make use of the primary key when evaluating the where clause. We have large number of columns, and obviously all these columns cannot be part of the primary key. Thus, queries on these columns will have to do full table scan, resulting in slower queries. In traditional databases, one can add secondary indexes to handle such situations. In ClickHouse, there is no concept of secondary indexes, but there is a special class of index called data skipping indexes, which makes use of Bloom filters and skips reading significant chunk of data that are guaranteed to have no match. Using all the discussed capabilities of ClickHouse, we built up a new logging pipeline, and we saw overall gain in every aspect. We were able to migrate one of the critical and major log producing application from our Elasticsearch cluster to a much smaller ClickHouse cluster. CPU and memory consumption on the inserter side also got reduced by approximately 8 times. Each Elasticsearch document, which was using around 600 bytes of data, we were able to bring it down to around 60 bytes in ClickHouse world. This allowed us to store 100% of the data in the newer setup, thereby removing the sampling completely. On query side, we also saw huge improvement in the query latency. To conclude the talk, Elasticsearch has served us very well over so many years. Elasticsearch is great for full text search, which ClickHouse doesn't provide. But most of the use cases don't require full text search capabilities. Everyone has different requirements, and you should evaluate what is the best solution for your use case. With that, thank you for listening to our talk, and we are ready to take any questions. Yes, please.
With Elasticsearch, I found that the number of documents by the number of fields kind of determines how many nodes or shards you need. And Index, have you found a similar situation with replicas and shards in ClickHouse where the number of documents and or number of fields has an impact on the size of the cluster?
Just repeat the question too for the stream.
Yes. So, if I understand the question properly, with Elasticsearch, based on the amount of the data, the number of shards and replica will change. You are saying, but in ClickHouse, does it happen similarly? So basically in ClickHouse, the main concept is partition, because like how ClickHouse parallelizes the things will depend on how many partitions you have. So you would like to not have too many partitions, also at the same time not too less partitions to get the maximum CPU. The sharding and replication, like those, the concepts in Elasticsearch world doesn't directly map with in ClickHouse world. Hope I answered the question.
Is there an ideal partition size in number of documents and or fields?
Right. In ClickHouse? So the question is there any ideal partition size? It will definitely depend on the size of the cluster, like how much hardware resource, like CPU, because CPU cores you have, because the number of partitions you make, the ClickHouse will try to parallelize those things, and how big is your cluster. Yes, please.
Yeah. Hi, I was wondering, did you find that you needed to make any adjustments to tune ClickHouse to be performant at the scale that you're operating at, around like the mark cache or any optimizations that need to be run?
So if I understand your question, like did we make any optimizations on ClickHouse clusters to ingest this much amount of data? We have a dedicated ClickHouse team who manages the ClickHouse cluster for us, and they have been managing for many years. One of the optimizations I would like to say is the file system you would like to use. Then basically, as we said, like so ClickHouse completely depends on the file cache, operating system file cache. So if you have a multi-tenant ClickHouse cluster, you will probably not use the file cache in the best way. So we actually gave a dedicated small cluster to this problem. Thank you.
All right. Thank you so much.